Hello and welcome to In Simple Terms with Satish. You reverse a car toward a wall. At first, the beeps are slow. Then they get faster. Then the car screams at you to stop. The car did not understand wall the way you do. It measured distance. That is the sensor story. So today let's answer directly. What is a sensor and how does it work? A sensor is a device that detects something physical and turns it into a signal a machine can use. More technically, a sensor is the measurement element in a system. It has an input quantity or measurand. For a parking sensor, the input is not danger, it is distance to a nearby object. It has a sensing element that reacts, and it has an output such as voltage, current, resistance, a digital message, or a simple on-off state. Engineers describe sensors by range, sensitivity, accuracy, response time, drift, and operating conditions. The parking assist system is the product. The sensor is the part that makes distance measurable. A computer cannot directly feel distance, temperature, pressure, light, smoke, or motion. It needs a translator. That translator is the sensor. A core part is often a transducer, something that converts a physical change into an electrical change. A common parking sensor uses ultrasound. It sends out a sound pulse above human hearing. That pulse travels through air, hits an object, and echoes back. The same sensor or a nearby receiver detects the echo. Now the system has a time measurement. Sound in air travels roughly 343 meters per second at room temperature. If the echo returns in about 6 milliseconds, the sound traveled about 2 meters total. Because it went to the wall and back, the wall is about 1 meter away. That is already a real sensor pipeline. Physical input, distance. Transducer, ultrasonic speaker and receiver. Output, echo timing or a distance estimate. Action, slow beeps, fast beeps, or stop warning, but the output is messy. Real-world signals are small, noisy, or in the wrong range. So many systems use signal conditioning. That can mean amplification, filtering, protection, or range shifting. In a parking sensor, filtering helps ignore weak echoes, electrical noise, and reflections that do not make sense. Then comes analog to digital conversion. Most real-world signals vary smoothly, but software works with numbers. An analog to digital converter or ADC samples the signal and turns it into digital codes. So changing voltage becomes numbers software can process. But numbers alone are not meaning. This is where calibration matters. Calibration maps raw readings to real units or useful states. For parking, calibration asks, how should echo time become distance? And when should the warning change? Set the threshold too sensitive and harmless reflections may trigger panic beeps. Set it too loose and the warning may come too late. Without calibration, a sensor is just producing data. With calibration, data becomes a measurement. Even then, sensors are never perfect. They have noise, drift, delay, limited range, and limited resolution. A parking sensor can struggle with angled surfaces, soft materials, dirt, rain, temperature, and strange echoes. So engineers rarely ask, what did the sensor say? And stop there. They ask, how confident are we and what else agrees? That leads to sensor fusion. A car may combine ultrasonic sensors, cameras, radar, steering angle, and speed. Phones and robots may combine accelerometers, gyroscopes, cameras, LiDAR, GPS, force sensors, and software models. Each sensor is imperfect. Together, they can produce a better estimate. Now go back to the parking example. The car did not magically understand wall. It measured an echo, converted it into a signal, turned that signal into distance, compared distance against rules, and then warned you. The same pattern shows up everywhere. It can rotate a phone screen, open an airbag, dim a display, stabilize a drone, trigger a smoke alarm, or stop a robot before it hits something. In simple terms, a sensor is the bridge between physics and software. The full chain is measurand, sensing element, output signal, conditioning, digitization, calibration, interpretation, and action. The big lesson is that sensors do not magically understand the world. They turn the world into signals. Engineering turns those signals into trustworthy decisions. If this helped you understand the topic in simple terms, follow or subscribe to In Simple Terms with Satish and share this episode with one friend who likes technology. I will see you in the next episode.